Good day, I am OROS from the Center for Asset Integrity Management. The purpose of this video is to serve as training for students to use the OROS Modal software along with the OROS OR35 analyzer that we have in our laboratories. Now, this video has got two focus areas, and the first is on actually performing modal testing, some practical tips specifically on using a modal hammer, and then of course on the modal analysis itself. Now if we have a quick look at our test setup, we have a 5mm aluminium plate, 600mm wide by 645mm long. We have freely suspended it on a piece of foam. We could have used bungee cords, but in this case foam was just more practical. We are going to use a single axis accelerometer to record our vibrations. Here I have a micro accelerometer from Diatran, 100 millivolts per G that we're going to use. And I specifically am using a micro accelerometer so that we do not unnecessarily mass load the structure. We are also going to use a modal hammer, a PCB model. And you will see that you can use interchangeable tips, and there are three tips that you have available. The first tip is a soft rubber tip that you typically will use if you're interested in frequencies up to a couple of 100 Hz, typically 200 Hz. Then you also get a nylon tip, as we have over here, that can give you excitations up to 2.5 kHz. There's also a steel tip available that will give you much higher excitation frequency bandwidth, up to 10 kHz is what you can expect with that. Now, in terms of our actual hardware, on the PC side, we have the Modal 2 dedicated desktop PC, which we've aptly named the Modal 2 PC, and with the necessary dongles installed for the licenses. And over here is our OROS OR35 analyzer. It connects to the PC via LAN, and there's a dedicated LAN port for the OROS, and that is clearly marked, so you can just connect it there. You need to use the correct IP settings, but that has already been set up on the desktop, but there is a document on the desktop for your reference. So if you have a look at the OROS OR35 analyzer, we have 8 analog input channels, all of them capable of powering an IEPE sensor such as the piezoelectric accelerometer that we have, and also our piezoelectric hammer. We've got 2 external inputs that are basically digital input channels, very useful for triggering and if you use something like a tachometer and shaft encoder on a rotor. But this is typically what you would use in the OROS NVGate software, which I'm not going to focus on today. And then we also have 2 output channels that you can use to drive electrodynamic actuators, for example. Okay, so let us load Modal 2. Now, something to keep in mind with Modal 2 is that before you can get to actually performing the modal test, there is some preparation work you need to do, but it is definitely worth your while, and it just makes the testing much easier and leaves less room for errors in terms of naming files, etc. So here is our startup screen. We're going to create a new project, so we click on create the configuration file, going to call it aluminium plate. Okay, so this is the screen that we are presented with. Under config there are a bunch of tabs, basically giving us summaries of what our project parameters are. So we can see typically a working directory here under general, coordinate systems over here, nodes, where we will
take our measurements, links for visualization purposes, as well as our degrees of freedoms. Also a tab for equations, but I will cover that later. Okay, so our first step is to find out geometry. Now, as I've mentioned, there is some preparation work that you need to do before you can perform the actual tests. And if you look over here, I've already marked out all the points I want to measure on my plate, and I've also chosen my coordinate system with the origin here at point 1, and if I've defined a matrix of 5 points in the width and 5 points in the length, giving me a total of 25 points, and also another point, number 26, that I will use as my reference location. I've chosen this location so that I'm not, so that my reference location is not on a nodal line of one of the plate modes that I'm interested in. So, to define our geometry in the software, we can either import the geometry if we have the point locations available in a universal file, or we can also define the geometry by entering the node locations manually. So for example, we can just say here append or insert, and I can just apply 1. So the first point will be at coordinate 0, 0, 0, and we can click here on geometry to display this point. But another location option to use, I'm just going to delete that point, is to define the geometry graphically. So if I click here on the geometry tab, it presents us with several options. We can create lines, segments, rectangles, ellipses, cubes, cylinders, cones, etc. And of course for our plate we can just select add rectangle. There are several options in terms of orientation of the rectangle, origin points, etc., Euler angles, and just the object properties. Now here the length corresponds with my width that I've defined, 600 millimeters, and width will be 645. Because I'm using a 5 by 5 matrix, that means I have 4 segments. Going to press apply, and then over here is my shape, and you can see already the software has also connected the lines, and we can display this the surface by clicking this button over here, switch between surface and wireframe. Now we can, by right clicking, click on coordinate to display the local coordinate systems that the software is now automatically defined, and we can also click on node numbers. Immediately you see that these node numbers do not tie up with my plate that I've defined, but we'll look into that just now. Of course, software did not add number point or point number 26, and that I can enter manually over here by entering the data just like that. Another option is to just copy and paste it from Excel. So let me just first delete all these points, all these coordinate systems. So I've already defined my points in Excel format, so I can just select the data. First column will be node number, second will be X location, Y location, and then Z location. So I just select that, Control C to copy, and go back to the software, click on nodes, and we simply say paste. And you can now see that my nodes have been defined, and we can display that, and you can see now it ties up with my definitions, and also at point 26. Now you can see if you just define the nodes manually, the nodes are not connected yet for visualization purposes, so we can connect them by defining lines or polygons. So just to demonstrate the polygon, we can click add a polygon, click on the nodes, left click, and then right click to terminate, and we can do this for all the points. And if you look over here on the links, you can see that it stores that entry over here. So again, you can manually define the links, but let me just delete that one, because of another advantage is that if you have defined that beforehand, you can also copy and paste it from Excel. So how the columns work is simply from your first node to the nth number of nodes that you need, and the software automatically just picks that up. So I'm just going to select all of these, Control C to copy, go to links, and Control V to paste, and you can see over here it automatically picked up that I have 4 3-node polygons, and the rest are 4-node polygons. And if you look now at the geometry, you can see they are all now connected.